Hello, my name is Lori Milliken. This lecture is all about statistical significance. So let me review the process of research. First of all, a researcher has a research question that they are trying to answer. In order to answer the research question, the researcher will design a study to test that particular question. So sometimes that research question is very specific to a certain population of people. And so that population is considered, and the researcher recruits a sample of people from that population of interest. Then they perform the study. They make all of the measurements, gather the data, and then they analyze their results using statistical tools, which we will talk about in this course, and then they make a conclusion based on those results. That conclusion is not a conclusion just about that sample of people. It really is about the population from which that sample came. That's the whole point of us doing research. We perform a study on a sample. This is a small group of people, or sometimes it's a large group of people, but it's still a sample. Those results are then generalized to the population. So in other words, we find that a certain drug is effective in the treatment of a certain disease in a sample of people. And then we say, well, if it's true in the sample, it must also be true in the population, and we generalize those results to the population. But the question really is, are the results accurate? How strong does a relationship have to be for us to be really confident in the results? Could it be a fluke? Could the result that we found in the sample be a weird characteristic of that particular group who we recruited? Did the results actually occur by chance? Is that possible? So whatever the conclusion a researcher makes, there's always a chance that that conclusion is wrong. Now I need to stress that even in situations where you have a very respected researcher who has used impeccable measurement tools, they've done everything correctly, there still could be a chance that whatever they found is not really what's going on in the population. There's always that chance, because there's always variability. There are always results that occur by chance. We try to minimize that, but you can't totally eliminate it. So there's always a chance that whatever conclusion that's made from one particular study, that conclusion could be wrong. This is where statistical significance comes into play. What is statistical significance? Well, if a study were repeated, what would be the probability that a similar relationship would be obtained? This concept is very important because we are trying to generalize the results from the sample to the population. And of course, we don't want to be wrong. An acceptable level of significance is p less than or equal to 0.05. And so we need to talk about what this actually means. So p less than or equal to 0.05. This means that if I conclude that a relationship exists between the variables that I studied, well, I could be right or wrong. That p-value is the probability that the conclusion is wrong if I generalize that result to the population. So a p-value equal to 0.05 means there's a 5% chance that I am wrong in concluding that there is a relationship or an association between those variables that I studied. So we need to talk about this truth table. And I just want to point out that there are two things that a researcher could conclude based on the results of their study. They could conclude that there is a relationship, or they could conclude that there's no relationship. So let's first focus on the conclusion that the researcher makes that there is a relationship. Let's say they measure two variables, they run the statistical test to see if these two variables are related, and of course these variables are being measured on a group of people, and that group of people is the sample, and they were selected from a population of interest. So the researcher makes the measurements, and they analyze the results, and they say, look at that, I think there is a relationship between X and Y, between these two variables. And so they write up their results of their study, they publish it, and they say, I conclude there is a relationship between X and Y. Of course, there is always a chance that they are wrong. So they could be right or wrong. The only way that they know if they are right or wrong is after someone else comes along and replicates their study and either agrees with them or does not agree with them. And so it's very important in research for results to get replicated. And typically what happens is a researcher will replicate some of the results of someone else's study and then expand the research question by a little bit. And so part of the study is about replicating or trying to replicate what someone else has found. And part of the study is really to move the research question forward a little bit and expand a little bit further, find out a little bit more. But there's always that piece that we're trying to replicate what someone else found. And so if I'm a researcher and I do my little study and I publish it and I say there is a relationship, I could be right or wrong. Other people will come along and replicate or try to replicate. And if they come up with the same conclusion that I came up with, great, it's correct. I made a correct conclusion. But there's always this chance that I'm wrong, and other people could come along, try to replicate my results, and they don't get the same thing. So that means that I was wrong in my conclusion. Not that I did anything wrong, but that result could occur by chance. Because most of the time, a sample that's selected from a population, of course we want it to be representative of the population, but sometimes it's not, because it's very, very difficult to get a randomly selected sample. And in fact, most samples are selected by non-random means. It's very difficult to do a random selection. So that sample of people may not be representative of the population. And when some other researcher comes along and selects another sample from the same population, their sample might be more representative of the population. So it could be that my sample, I got a certain result, but it doesn't represent the population, so I make this error. And someone else comes along, and maybe several other people come along, try to replicate the study, and they find that they got a different result than I got. And so, bottom line, when you conclude there is a relationship, you could be right or wrong. Other people will come along, try and replicate your results, and if we all agree, then I've made the correct conclusion. If everyone else gets something else, the opposite result, then I know I made an error. And this is called a type 1 error. This error is given by that p-value. And before I said the p-value should be less than 0.05. 0.05 or less. There's also the other conclusion that I could make. I could conclude that there is no relationship. I didn't find any relationship between X and Y. Of course, I could be right or wrong about this conclusion as well. And I don't know until someone else tries to replicate my results. So if I find no relationship and everyone else does too, well then I know I've made the correct conclusion. But if I said there's no relationship and everyone else comes along and says, oh no, we found one, then I know I was wrong. This kind of error is called a type 2 error. So when you conclude there is no relationship, you risk a type 2 error. When you conclude there is a relationship, you risk a type 1 error. So here are these two kinds of errors. If you think the relationships that you found in your sample of people is strong enough to conclude that there is a relationship, you risk making a type 1 error. And a type 1 error is when you conclude there is a relationship when there is not. And that is only demonstrated by future studies that will either agree or disagree with yours. So that's type 1 error. The other kind is type 2. If you think the relationship is not strong enough to conclude that a relationship exists, so you're saying there is no relationship, you could be right or wrong about that. You risk creating a type 2 error. And a type 2 error is when you conclude there is no relationship when actually there is. But you don't know that until other people come along and replicate your study. I need to introduce to you a term that is called the null hypothesis. Some people in research articles will talk about this null hypothesis, so I want you to hear about what it is. And this is the assumption that there is no relationship between the variables that you are considering. And many statistical tests are based on the fact that the null hypothesis is true. So this is like very similar to our legal system, where someone is innocent until they are proven guilty. You assume they're innocent until you gather up enough evidence to prove otherwise. In statistics, it's very much the same. You assume that there's nothing going on until you gather up enough evidence to suggest otherwise. So often people will talk about the null hypothesis. Based on my results, I either accept the null hypothesis or I reject it. So here is that same table again, except now I've put in the language of either accepting the null hypothesis or rejecting it. So now I have to say that this can be a little bit of a brain teaser here, so don't be too hard on yourselves if you don't get this right away. This might take a little bit of repetition to actually understand it. So give yourself a little bit of time. You may need to come back and listen to this slideshow again for you to really understand it. But this is the same table, except I've layered on some new language here. So that first row, I conclude there is a relationship. When I conclude there is a relationship, I am rejecting the null. And the null says there's no relationship, so I reject it because I'm saying there is a relationship. Again, I could be right or wrong. If I'm right, good for me. If I'm wrong, I've made a type 1 error. The other case is where I conclude there is no relationship, so I accept the null because the null says there is no relationship. If I'm wrong about it, that's a type 2 error. So these type 1 and type 2 errors are actually related to one another. Some researchers in the past have said, well, I really hate being wrong. This p-value of 5.05, the 5% error rate for a type 1 error, some people said, well, I don't want to be wrong 5% of the time. I want to be wrong only 1% of the time. So in those cases, some researchers would only say things are significant if the p-value came out to be really, really small, like 0.01 instead of 0.05. But when you do that, you actually reduce the type 1 error at the expense of a type 2 error. And so those researchers who try to adopt a more stringent cutoff for saying something is significant, they did so at the expense of increasing their type 2 error. So now this p less than or equal to 0.05, this is a very well accepted criteria for calling something statistically significant. So what happens is when researchers collect their data and they analyze their data, they use some statistical tools to see if the result is significant. This p-value is generated by the software people use to perform statistics. So you get the result of your statistics and you get this p-value that tells you how significant the result is. Most people use this cutoff of 0.05. If the p-value comes out to be a 5% error rate or smaller, we are going to call it statistically significant. Some researchers moved that cutoff to be more stringent, the 0.01. Instead of a 5% error, I'm going to accept a 1%. But if you think about this, that researcher who's doing a whole bunch of research, more of the time they will be calling something not significant if they're moving their criteria to 0.01. So all of their research studies where they get a p-value of 0.04, 0.03, 0.02, they're calling all of those results not significant. When you call a result not significant, you risk the type 2 error. And so these researchers who tried to protect against a type 1 error, they did so at the expense of the type 2. A type 2 error is also related to something called statistical power. Statistical power is 1 minus beta, where beta is the rate of committing a type 2 error. So we have two errors, type 1 and type 2. Type 1 is given to you by the p-value. It's also called alpha. A type 2 error is the other kind of error, and it is called beta. Statistical power is related to a type 2 error by 1 minus the type 2 error. So we also have acceptable rates of a type 2 error. So just like a the type 1 error acceptable rate is 5%, the type 2 error rate, the acceptable level is 0.2 or 20% or smaller. So if power equals 1 minus beta, and beta needs to be 20% or smaller, that means that power needs to be 80% or bigger. So statistical power is important because we want a high power because that means a low beta or type 2 error. And there are a couple of ways to decrease this error rate, type 2 error. You can actually increase the type 1 error, so the same conversation that we had about reducing a type 1 error at the expense of a type 2, you can actually reduce the type 2 error at the expense of a type 1. The other way to decrease your type 2 error rate is to increase the sample size of the study. So here's the bottom line. If you want to minimize both of these kinds of errors, you need to do a couple of things. First, adopt a reasonable type 1 error rate, which is the p-value of 5% or less. And you need to ensure that there was an adequate number of people in the study so that if a relationship was there to begin with, you have enough people to detect it. So you ensure that your sample size is large enough to detect a relationship if it's there. That protects against type 2. And you go with a reasonable p-value cutoff, which protects against a type 1 error. Now, in the second half of the course, we will be looking at experimental research and statistical tools that allow us to determine if means are different between groups. And so, many times we perform studies comparing groups rather than quantifying associations between variables. So the question is there a statistically significant difference between groups? And you'll see this often where people are trying to apply a treatment to see if it's effective. And so you have one group that gets the treatment and another group that gets usual care, or they're the control group. And so at the end of the study, these groups are compared, and if the groups are different, that means the treatment had an effect. We can do the same thing here. The null hypothesis is the assumption that there is no difference between these groups, or that there is no effect of the treatment that you applied. Again, similar to this innocent until proven guilty, there is no effect of a treatment until we gather enough evidence to prove otherwise. We can have the same truth table, it's the same layout, type 1 and 2 errors are in the same places, except now we're concluding that the means are different or the treatment had an effect, or we conclude that the means are the same, the treatment did not have an effect. And so there's still this type 1 error or a type 2 error. If we conclude that the treatment had an effect, we could be wrong. If we conclude the treatment had an effect, we risk making a type 1 error. On the other hand, if we conclude that the treatment did not have an effect, we risk making a type 2 error. We could be wrong about that too. So the p-values that I'm talking about relative to this type 1 error, these p-values are generated by the statistical software packages that researchers use. Some examples are SPSS, another is SAS. These are statistical software packages that perform our statistics for us, so we don't have to do them by hand. This p-value is generated along with the results of those statistics, and you'll see these p-values reported in research articles. These p-values depend on the strength of the relationship, meaning if it's a stronger relationship, it's more likely your p-value will be small. Or if you're talking about experimental research, if you have a bigger difference between groups, then you're more likely to see a small p-value. The p-value is also dependent on how much variability is in the measurements that you make and how many people are in the analysis. You can calculate these by hand, and there are some p-value tables that you can use to determine the level of statistical significance as well. Most of the time, researchers use software. So the bottom line, here's what you should know. You should be able to describe and explain what statistical significance is. You should be able to tell me what a p-value means, so a p-value of 0.05, what does that mean? You should be able to tell me the difference between a type 1 and a type 2 error, and you should be able to describe how these two errors are related to one another. When you try to reduce one, you can possibly increase the other and vice versa. And finally, you should be able to tell me how you minimize both of these types of errors.